Thank you very much for coming back after the coffee and being almost in time because we are in the south of Italy, as you heard, and I think we don't have to spend too many words anymore to say how beautiful is Italy, how nice is Italy from the culture point of view, but also from the science point of view and music. So we have a full week to enjoy this. And as Italian originally, I can only say that, I'm from the north, but it's beautiful. Italy is beautiful. And after so many words about Walter and his performance, to introduce his keynote, I would like to remind something that maybe not everybody knows about Walter. He just gave me his reference this morning that he's probably the only one that was present at every AMS conference, from the first one, and he's going also to Guilina now, so he's keeping going, and he's becoming, a kind of column in this community of C14, AMS, and so on. And I'm very happy to invite you to give us your keynote. In this world where artificial intelligence is taking over our talking, we never know on the telephone if now is a person or not. Having your keynote about reading and interpreting the isotope language. I hope that the artificial intelligence is not yet ready to fake Walter.
I'm in a way speechless after this performance on the piano. I've never heard in a long life such a talent at that age. I attended recently a competition of young people in Salzburg, and all of the people of the age of this player and younger were from Asian countries. So to see somebody from one of the countries where music originated in a way with such a young age and such a talent was just mind-boggling to me. Okay, I have to give a talk which I suggested as one of several topics to Lucio and Gianluca, but somehow they chose this very general talk. Of course, I know this is impossible to describe this whole field in all its different facets. So I will try to do the following. First, I will talk about some of the pioneers which I admire in the field of isotope research. Then after that, I will jump to very recent times, the last few years, and I was amazed on a few topics which caught my mind at least, and I will give you a few examples. This is, of course, a very subjective selection of topics, but within the time given, it's not possible to cover the whole field. So let's start. The person who initiated this word of isotope language was actually Hans Oeschger. He told me a couple of years ago, when he was still alive, perhaps someday we will understand the climate through the isotope language. Of course, this is a very great statement, and we all know in this room that isotopes are being used in various fields as a means to understand more about our climate. Now, in fact, I played music with Hans Oeschger many, many years ago at AMS 4 in Niagara-on-the-Lake. And this was in 1987. So if I did do the calculation right, it's 37 years ago. I played a Vivaldi concerto together with Hans Oeschger, and the guy on the piano is John Ruckledge. Some of you may know him from Toronto. Now I will just switch to a few pioneers of stable isotope language. And of course, again, this is a choice I just took. Who was perhaps one of the important people at the very beginning was Harold Urey. Harold Urey discovered the deuterium in 1932. This was the year when Chadwick discovered the neutron, in the same year. So Urey didn't know anything about neutrons. He just did actually not mass spectrometry, but optical spectrometry. In a discharge of hydrogen and also enriched hydrogen, he was looking for a faint little signal in his spectra of the Balmer series. Yeah? And he also, later he tried to estimate the relative abundance of deuterium in hydrogen. And I think he got it a little too low, the number, because at that time the first mass spectroscopists also started to look for it, and they found a number which was a factor of almost 10 different from what Urey was originally arguing. But on the other hand, he was clearly the discovery of the deuterium as the first person, and that earned him the Nobel Prize in 1934. Now, for those who are in mass spectrometry, one of the real pioneers, he is sometimes called the father of mass spectroscopy, is Alfred Neer from the University of Minnesota. And I mentioned one particular discovery. At the time, it was known potassium is radioactive. But what is the radioactivity of potassium? It's not the main isotopes, which are stable, 39 and 41. So he did the mass spectrometry, and he found this 10 to minus 4 abundance little peak in his mass spectrum. Everybody thought, well, this is probably calcium-40. But he was very clever. He actually had an ion source where he changed the impinging energy of the electrons. The ionization potential for potassium is different than for calcium. And in this way, he could confirm that this little peak, which he saw between the huge peaks of the stable isotopes, that it is potassium-40. Now, the interesting story of potassium-40 is as follows. When Carl Friedrich von Weizsäcker, who was experienced in astrophysics already at the time, in the mid-30s, when he heard that potassium-40 is radioactive, he thought, well, we know the radioactivity of potassium-40 is the beta decay to calcium-40, but perhaps there is a different decay to the other side, to argon-40, and perhaps the overabundance of argon-40 in the atmosphere is due to this decay of potassium-40. And he even made an estimate of the half-life. He estimated if all the argon-40 in the atmosphere comes from potassium in the Earth's crust, giving off argon-40 over billions of years, then the half-life must be in the order of a billion years. So his estimate of the half-life was even correct. It's a fantastic little paper. I only know the German, it's in a German journal, but it showed already at that time that somebody who is able to connect different fields can find out something which you never think of. So it is actually the dual beta decay what he discovered, Weizsäcker, when he heard this result from Otto Neer. Now, the next person, of course, should be well known in Italy. Cesare Emiliani did his undergraduate and first graduate work in Bologna, and then he moved to America, to the University of Chicago, and did his PhD together with Harold Urey. And Cesare Emiliani stayed all his life in America, later moved from Chicago to Miami, and he developed the Delta 018 method analyzing foraminifera in deep sea cores. And this was the first hint which he found that there is some cyclic timing of possibly ice ages, following the famous theory of Milankovitch, who, you know, I mean, most of you know that, of course, the Milankovitch theory, which says that the ice ages are triggered by the changing of the orbital parameters of the Earth around the Sun. There are three different contributions to it. I can't go into detail of that. But this was the first hint. Interesting enough is that when the ice core measurement started, Cesare Emiliani, he always thought the signature he can read on oxygen 18 has to do with temperature. And it turned out that's not the main effect you see even in the deep sea sediments. It has to do with the fact that if there are glacial times, isotopically lighter water is being transported to the land and deposited there. The ocean goes down by 100 meters or so and gets heavier, isotopically heavier. This is something he was not considering as a good explanation at the time. This is what other people said who worked in this field. In addition, he was convinced that the cycle is 40,000 years and not 100,000 years of the ice ages. Both of these assumptions, in a way, were wrong, but he was still the pioneer to develop the method as such. Okay, the next person is perhaps not so well known to many people of you, but Fritz Houtemanns was actually the predecessor of Hans Oeschger in Bern. And he had a very, very checkered life, really. But what was interesting is that he started essentially isotope geochemistry in Bern, and Oeschger was his follower. And so he did the first correct estimate of the age of the Earth at the time by using material from meteorites, which showed the original uranium to lead ratio. If you take this fine material on the Earth and try to find the original lead to uranium concentration, you would not find the right, because there's always some decay already happening from uranium into lead. Anyway, this was Fritz Houtemanns, and the last one on this figure is probably known well to you, Willy Danskart from Copenhagen. He really was the father of ice core research, and all his life he worked on ice core climate research, and he figured that delta O18 and delta deuterium is so useful to follow the different ways the climate is printing its history in the ice cores. Okay, I have another picture here which shows Fritz Houtemanns at his later age discussing with Harold Urey in Bern. Harold Urey was considered to really be the great first person to understand all the effects of stable isotopes. Now let's switch quickly to some pioneers of radiocarbon in the decay counting era. Of course, Willard Libby has to show up, who invented carbon-14 dating, again at the University of Chicago in 1947. He rightfully received the Nobel Prize in Chemistry in 1960. There was another person close to him. Jim Arnold was actually his student. And Jim Arnold, his paper shows the first radiocarbon measurements on samples of known ages. And this famous paper showed the first time that radiocarbon dating may actually work. Yeah? This was not known for sure at the time. Next is Hans Suess. Hans Suess was actually a nucleophysicist, was involved in the shell model development early on, and later he switched to radiocarbon and was interested in the effect of fossil fuel on the carbon-14 content in the atmosphere. In 1955, it's now generally called the Suess effect, and as we may hear later in this conference, Of course, the fossil fuel effect continues. It continues all the time. In fact, CO2 is continuing in the atmosphere, and also this effect on the carbon-14, because we add dead carbon to the CO2 from fossil fuel. Okay, the last person on this list is Hessel de Vries from the University of Groningen. Hessel de Vries was, in a way, almost like a meteor who burned out very, very early. He had a tragic life. In fact, he killed himself because of a love story. This happens even in Holland, not only in Italy. He killed it. Anyway, but Hessel de Vries was the first one who observed that carbon-14 is not smooth over the years, and sometimes it's called de Vries wiggles, this effect. So he was the originator of the effect, the fact that carbon-14 is not constant over all times. And that, of course, gives us big trouble in the calibration. Okay, so these are the original people with radiocarbon, and I'm now switching to some radiocarbon pioneers in the atom counting era, the EMS era. And again, some of you know the people very well. One is Rich Muller from Berkeley, who did the first measurements on a cyclotron with carbon-14. Very difficult because he used positive ions and he had to get rid of nitrogen, and this was a tour de force. Rich Muller, by the way, was a student of Luis Alvarez. And Luis Alvarez initiated using the cyclotron as a mass spectrometer originally because he asked Richard to help him. Luis Alvarez was an old man at the time, but Rich Muller should help him to look for quarks, for free quarks, using the cyclotron, tuning it to masses which do not exist regularly. But then he actually found that you could use it for carbon-14 dating. Now, the other people you also know very well, Harry Gove, who actually organized the first AMS conference in Rochester in 1978, where I had the good luck to be present there. And there were several other people in the same year of 1977. All of these people in 1977 published papers. Ted Litherland from Toronto, and also Ken Purser, who later became so important in producing AMS facilities. They together used the tandem accelerator in Rochester to measure carbon-14, and then there was Earl Nelson at McMaster University in Hamilton, and these people really established the AMS technique in 1977. Okay, now if we look at the summary of elements and isotopes, just in general, I have this information from the nuclear chart, which just came out in 2022. Well, we all know they are stable and radioactive elements, and the total number of elements is 118. If you look at isotopes, well, it's clear that there are many more radioactive isotopes than stable isotopes. Total of about 3,300, and they're still continuing to get more of them. The extremes are also somewhat interesting. The largest number of stable isotopes per element has 10 stable isotopes, and the largest total number of isotopes per element is actually mercury, which is 47 isotopes. The smallest number of isotopes per element is oganesson. Of course, this is the heaviest element we know, and only one isotope so far has been observed. And there's a big effort now going on, again also in Berkeley, not only at GSI and Dubna and also RIKEN in Japan, but also in Berkeley. They rejuvenated their program to look for element beyond 118. It mainly has to do to get targets available, very heavy radioactive targets which you could bombard to reach out into this region beyond element 118. Okay, now I'm switching to some recent highlights which I find interesting, but again, this is a very personal sort of choice. let's start with something I consider in a way a quantum leap in radiocarbon dating, the famous Miyake events. Unfortunately, Fusa Miyake is not here, but I'm sure she will show up at the AMS 16 conference in China. This is absolutely amazing. If you worked in radiocarbon for many years and you know how many troubles you have in calibrating and finding sometimes regions which are impossible to be used for precise carbon dating, these Miyake events were really something very exciting. This is a picture of Fusa Miyake, and this is the famous picture which she showed in 2012, already 12 years ago, that there is an excursion in Japanese cedars if you analyze them year by year. And this excursion happened in just 1 year. And this is an absolutely fantastic signal. If you can measure it in 3 rings, of which you know the absolute age, you have a fixed point in time for carbon-14. If you find this signal in other material around the world, if it actually shows up around the world, then this is something, oops, sorry, this was too far. Okay, so this significant 1-year excursion of carbon-14 were measured in 3 rings of Japanese cedar, and there was a second one in 993 AD after the first one. Both were published by Miyake in Nature Communication. Then, in the ensuing years, these events were confirmed in 3 rings from 5 continents. So it was a global event, not a local event. This was very important. And then, from then on, a number of other observations were made, and also some interesting applications. The one very interesting, I found at least very interesting, was the evidence for Europeans in the Americas. On the left side, you see a global map, and it is suspected, was suspected, that the Vikings, or some people related to the Vikings, were the first one to reach actually Northern America, Newfoundland. And this lady on the bottom, she actually did excavation in the 60s at a site which showed to be man-made. And later, many years later, in Groningen, they measured material from this site, and they found very clearly in these 3 rings which they measured from this time, they found the signal of the 993 AD event, this strong increase, and going out of these trees to the felling date or waning edge, they could actually determine the time when this material was used back in 1021. So they argue that now they know within 1 year when the first Europeans arrived in America. Interesting story. So the next one just came out recently, is an absolute dating of a Neolithic site in northern Greece. This has to do with an excursion which was observed previously in the year 5200 BC, so quite some old time. To this day, by the way, one does not know for sure what the cause of these excursions are. The general assumption is it's energetic particle outbreaks of the sun, so sometimes called solar storms, and but it's not absolutely sure, and especially one doesn't know where they come. They're completely random. There's no theory which says the sun has to erupt at a certain time to make these high energetic particles. Okay, so this site in northern Greece, to the left you see which part of Greece is being investigated. There's some lakes, and there's an old site with a lot of trees. And within these trees, they very clearly saw the signal from 5,200 years BC. This 1-year excursion, and having several trees with 3 rings and measuring year by year, they could very well establish, fix the date of this particular archaeological site. The last example is actually, I'm not sure all of you have seen this paper. It's not so easy to see these papers. This is by the French group around Edouard Bard, that they found a carbon-14 spike in the late glacial period in southern France. This is in absolute time, this is 14,000 years ago. Okay, thank you. Sorry. Oh yeah, this is Edouard Bard. Yeah, Edouard Bard led this particular investigation where they actually collected a number of trees which apparently are preserved in sediments, river sediments for a long, long time. And they found this spike here at 14,300 years before present. This is the oldest spike, to my knowledge, which has been found, and this allows now, again, to use it for other applications. I don't know which one. Okay, I want to mention an archaeological highlight, to me at least. This is by pure accident. I didn't know that Elisabetta would be the chairperson here, because that's something I admire in the sense, is it really possible to establish accurate dates, absolute chronology of the kingdom of Judah? This is during the Iron Age, and all people here know that the Iron Age has this plateau, and it's very difficult to do any precise measurements. But this group around Elisabetta, they did a tremendous job in actually digging into old remains in Jerusalem. How to get access to this is another story. In any case, you see the calibration curve and this complicated structure. And by using very, very detailed studies of the material which they found, the term of microarchaeology is being used by her group. And this seems to be possible to actually establish an absolute timing for this period. I cannot talk about anything in this field, but Elisabetta is here. You can ask her if you have questions. And they published this paper just recently. Now, the carbon-14 bomb peak, of course, is something very familiar to everybody here. And there are many, many applications. I once gave a talk and called it the ugly and the beautiful. And you know that, of course, that the carbon-14 peak was produced by the atmospheric nuclear weapons testing. The one thing I always like to point out is, because it's rarely shown, when you actually generate carbon-14 as a new atom by the reaction of neutrons with nitrogen producing carbon-14, either through cosmic ray neutrons or neutrons from the atomic explosions, it goes through a two-step process before it turns up to become CO2. This I learned from Paul Crutzen. He told me that it's not a direct oxidation of carbon-14 to O2, but it actually goes through an intermediate step, first producing carbon-14 oxide, monoxide, and then in a second step with the OH radical, the CO2. So it is a sensitive measure. The carbon monoxide actually is a sensitive measure of the OH radical concentration in atmosphere. We had a program on this. But in any case, I just want to point out, don't believe these figures which always show carbon-14 generated and then CO2. It's not directly produced. There's a two-step process. Okay. Now, the one outstanding thing I feel in the use of the carbon-14 bomb peak, and we hear probably more about this later in this conference, especially in connection with forensic studies, the one outstanding thing I found was determining the age of cells in humans. I actually saw this in note in the newspapers in Vienna. And when I saw it, I immediately called the lab in Stockholm. And in this special department of cell and molecular biology at the Karolinska Institute, famous institute, you know that they always determine who gets the Nobel Prize in medicine. They had this fantastic idea, which is given in the first paper. Please read this with me. Most molecules in a cell are in constant flux, with a unique exception of the genomic DNA, which is not exchanged after a cell has gone through its last division. The level of carbon-14 integrated in genomic DNA should thus reflect the level in the atmosphere at any given point, and we hypothesized that the determination of carbon-14 levels in genomic DNA could be used to retrospectively establish the birth date of cells in the human body. Yeah? This is a fantastic theory of biologists, yeah, that this could actually work. Yeah. And here you see what can work. There's the bomb peak, of course, the carbon-14 excess through the bomb. And you see a person with a lifespan of something like 60 years. And if you measure, extract cells after the person died and determine the carbon-14 content in it, you find that different parts of the body point to different times of his life or her life. And so this is a fantastic method to actually find out when cells are being born. We did one collaboration with this group some time ago where we investigated the olfactory bulb in the brain, the smell center, yeah? It turned out all the people we investigated were 5 individuals. They were born before the bomb peak, and none of them, 60, 70 years later, showed any increase of carbon-14 in the cells of the olfactory bulb. That is, no new cells were produced after birth for the olfactory bulb only. But then they had this one fantastic paper where they showed that in one of the most important parts in our brain is the hippocampus, where memory is being stored and many other things. And what is shown here on this, more than 50 individuals were investigated, and these experts in biology, they can actually separate neuronal cells from non-neural cells of the brain. And what is shown here is that every point is the birth date of the person, yeah? And if the signal is above for people who were born before the bomb peak, is above the birth date, that means that some cells were formed later in life. On the other side of the peak, you see that it indicates if the signal is below, that it points to a later time in their life. And so they clearly showed that there is some new cells, neuronal cells and non-neural cells are being made in adult. This is very important, of course, for any brain damage. Okay. Now a question, I'm supposed to talk about the climate, but a question relevant to climate change is this question. Was Greenland nearly ice-free at any time during the last 2.5 million years? And there are people who investigate this. And the two papers which came out also not long ago, one actually very recent, one is Jörg Schäfer from the Lamont Doherty Earth Observatory, and the other one is Paul Biermann from University of Vermont. In short, what Schäfer did, they investigated material on the bottom of ice cores, the rocks on the bottom of the ice cores, and they measured beryllium-10 and also chlorine-36, both, aluminum-26, sorry, beryllium-10 and aluminum-26, and it was clear that only this material the bottom rock can contain this if there was no ice. So the cosmic rays can actually produce these isotopes. And if you find out actually the ratio of aluminum-26 to beryllium-10 allows you actually to do some dating in a way, because they have two different half-lives. Beryllium-10 half-life is about factor of 2 longer than aluminum-26, and so the ratio changes as time goes on. And it's at the beginning, this ratio is known pretty well. It's something like 6 to 7, and then as a function of time, with a effective half-life of 1.5 million years, it's getting smaller and smaller. So from that, Jörg Schäfer and his group concluded that Greenland was nearly ice-free. Now this guy, Paul Biermann, actually first argued against this because they investigated sediments, and sediments off the coast of Greenland, and they didn't find any evidence that there was no glacier covering Greenland for a long time. But in a recent paper, they actually changed in a way. They confirmed the ice-free thing by finding plant, insect, and fungi fossils in the bottom rock material, of ice cores in the center of Greenland. And so there is quite likely that at some point Greenland was ice-free or partly ice-free. And as you all know, if all the ice of Greenland melts, the sea level will rise by 7 meters. By the way, if all the Antarctic ice will go away, it will be another 70 meters. So at that time, we will be drowned. Maybe even this in Lecce, you will be drowned. Okay, so this is now an event which actually did change the climate for sure. You all know that. the famous meteorite or asteroid, whatever you will want to call it, which killed the dinosaur, people estimated that it must have the size of Mount Everest, the meteorite which came down to the Earth. And that did indeed some damage to the climate. In fact, it is well known or accepted that the dinosaur died out in 66 million years ago. Why do I show this thing? Because very recently, they did an intensive mass spectrometric study, not with AMS, but with ICP-MS, with high-resolution ICP-MS, for ruthenium isotopes in this layer, which supposedly was produced by the impact worldwide. And if you look at the figure to the left, please notice at the bottom, if you can see it, this is not delta notation, but epsilon. Epsilon is a factor of 10 smaller than delta. It's 10 to minus 4 in units, epsilon. And they measure fractions of epsilon. So the precision must be tremendous to actually establish numbers on this figure. And what you see is that the green and the red line are meteoritic types, which are different from the material which they apparently collected from this impact of the dinosaur-killing asteroid. And so they are quite sure that it does not belong to this other type of meteorites, but belongs to a so-called carbonaceous chondrite, probably originating from the outer solar system. Okay. Now, a very recent event. This is the last special thing I show. A very recent event was actually a meteoritic fall, which happened beginning of this year in Germany. Not far from Berlin. It just missed Berlin by 50 kilometers to the west. Now we had a talk given in Vienna by one of the people involved in that, and he told us about this worldwide observation system. The sky is being studied, being looked at all the time to find possibly something which actually comes down to the Earth. Most of the small meteorites, never reach the Earth, but this one was big enough, so they actually came down in this special place. So this is the field which where all these breakup products of the meteorite were collected, and you see the samples were from a few gram to down to 1 gram material. And this paper was published just recently in Meteoritic and Planetary Sciences. So Tim Joule should know that, of course, very well, and the discussions about it. Why I'm showing this is because, for me, this is an experiment which used the whole machinery of isotope methods. It's just amazing if you look at this list. It used almost any method you can imagine, yeah? Electron microscopy, electron microprobe analysis, inductively coupled plasma, atomic emission spectrometry, inductively coupled plasma sector field mass spectrometry, gas source mass spectrometry for oxygen isotopes, multi-collector inductively coupled plasma mass spectrometry for titanium isotopes, then noble gas mass spectrometry for helium and xenon, and gamma spectrometry in an underground lab near Dresden. Also AMS measurements. In fact, these two measurements were performed in Vienna for aluminum-26 and calcium-41. Magnetic susceptibility measurements and Fourier transform infrared spectroscopy, where you can identify materials. So it was an absolutely astounding collection of measurements being performed on this very unique fall, which was actually being observed. A small thing, why it has this very strange title, yeah? Cosmic Peers from the Havilland. Riebeck. There's actually a connection. This, of course, is only well known in Germany. There was a famous poet who made a poet about exactly this area, a very rich person who lived in this area, and he gave, his custom was that he gave to the children pears every year when the pears were ripe, yeah? He gave it off. And when he died, his son was, he expected his son would not continue this trade. So he asked that a pear were put in his grave on his sarcophagus, and out of this grew a new tree and produced the pears which the children could still take. So this is the connection to this title, Cosmic Peers. In this case, it was a meteorite, not the pear which came down just at this point. Okay, I think I'm at the end, more or less. I want to close with a statement of two great earth scientists, I would call them. The one we talked about already, Cesare Emiliani. Please show hands if you have ever seen this book which he has written, Planet Earth. Anybody knows that? Nobody. This is an absolutely amazing book. I came across it just recently. He wrote it at the end of his life in 1992. It has 700 pages and describes the whole Earth in a detail you wouldn't believe. It starts from Big Bang and ends up with the creation of life. And it is just amazing, his knowledge about the whole world, which he's written down in this book. And he says it is written for, not for laymen, but there's not much mathematics in it. It's written in a beautiful way. And I just showed this few sentences in the preface. He said, our planet is at risk. The current explosion in the human population is forcing us to a simple but pivotal choice: stabilize the planet or perish. The first few decades of the next century will bring grave crisis. And while this was 30 years ago, this book was written. Environmental, economic, human. Only if we achieve a close understanding of the system of which we are part, how it came about and how it works, will the next generation be positioned to cope with the emerging problems. Okay, and the last person whom I met personally is Paul Crutzen. Paul Crutzen actually wrote a paper which was published in the year of his death, and it turned out to be a paper which was published. You see the reference. He got the prize in Russia, at the time, and the paper is called "We Live in the Anthropocene, So Will Our Grandchildren," and there he makes the following statement at the end: "Our curiosity and eagerness to understand everything surrounding us, including ourselves, makes science overturn each and every stone. At the same time, it is difficult to escape the impression that at the present stage of the Anthropocene, which we unfortunately cannot refer to as the early Anthropocene, not knowing how long it will last, humanity as a geological force seems to be somewhat unbridled and helpless. To children and young people, 87 years, he was 87 at the time, seem an eternity. At the age of 87, one sees this differently. Nonetheless, let us hope that through the acceptance and awareness of our epoch, the Anthropocene, 20 years after the first little publication about it in a newsletter, the actions needed to limit major irreversible damage to our planet, especially the many serious effects of global warming, will now gain the required momentum." Let's hope that he is right. Okay, that's the end. I have nothing more to say. Thank you very much.
Thank you, Walter, for this enlightening opening talk. Any question for Walter?
It's time for lunch.
Walter, I have a question for you.
Yeah, okay.
You mentioned so many people and you explained to us a lot of their science and their input. What is your vision for the future? Can we put your picture there and quote you? Mm.
I think, well, what can I say? I can actually only quote my wife, who always quotes Einstein. And Einstein said, you can either consider the universe as friendly or as hostile. So if we accept that the universe is friendly to us, then that's the only hope we have. So we will continue to live. And every time, especially now, of course, at my age, I'm fortunate to actually have already a great-granddaughter and see the new life is the only answer we have. Everything else is going away. People are still killing each other to the thousands. But new life, you cannot do anything. It will persist. And when we saw this young boy playing this beautiful music, I mean, this is another indication that life is going on. Yeah. That's the only answer I have. Sorry.
So for this conference, we decided to have three prizes. So the first one was given by director. Director is not here, but probably will come during the week because he's abroad. And the winner is, for this prize, Walter Kutschera. Please stand up. By director of this university. You can open, Gianluca. This is the seal of the University of Salento to Walter Kutschera. Okay. professor of the University of Vienna, founder of the Vera Laboratory for the fundamental contributions in isotope physics and accelerator mass spectrometry. Professor Fabio Pollice, rector of this university. Congratulations.
Yeah, then we also decided to award 2 prizes, which will be decided across the conference. One is for the best oral communication, and another one for the best poster. And Tim Jewell will chair the committee for the selection of the 2 presentations. They are intended mainly for early career scientists. And of course, the committee will be the International Advisory Board. And on Friday, the closing ceremony, we will announce the winners.
It's for early career scientists. I don't know what early means, probably much less than the radiocarbon half-time, for sure. And there is an additional award. I just decided this night for this. You see on the back of your badge, there are a few sentences, Italians and also a dialect. Usually when you do the presentation, you finish saying, okay, thank you for your attention, and so on. There is an innovation in this conference. If you want to participate to this award, you have 2 possibilities. Instead of saying thank you for your attention, the first possibility that you have is this one. It's on the back. You cannot miss. Okay? You have to see. Everything is recorded in this conference. You see, there are different cameras. At the end of the conference, the first possibility is this. If it's too difficult for you, I give you a second possibility, which is also on the back of your badge. The second possibility is this. You decide what to do, okay? So Lucille, for sure, will say it. And there is a name for this award. At the end of the conference, the award will be the Golden Ugula Award for the best singer of the conference. Okay? You have time to think. I think now it's better to have the other scientific session before lunchtime. Okay.